See, now we have different kinds of point defects. As I told you, we have vacancy defect, we have interstitial defect, we have Frenkel defect, and one more we have Schottky defect. So these are the different, you can say, the point or defects which we get to see in solid crystals. Now when we talk about the vacancy defect first, right. So what is vacancy defect? As the name suggests, vacancy means vacant spaces, right. So what you get to see, that when you see a crystal lattice, it's like that, right. Suppose I am drawing a crystal lattice, say of any crystal, particularly non-ionic solid, right. So what I get to see, that here so I'll draw one more you can say dimension. So when I see, what I get to see, that there are certain vacant spaces here, right. Suppose this place is vacant, suppose this place is vacant, suppose we get this place is vacant. So what we get to see, that few particles are missing from their position. That means we get to see a vacant spaces, right. So that means there exists a vacant space. So when there is a vacant space, that means it is a loss in mass per unit volume. So as a result, what happened, density of solid, this kind of solid showing this vacancy defect, decreases. And you know what kind of solid actually show this kind of imperfection? That is shown by particularly the non-ionic solids. It is shown by the non-ionic solid. So if somebody is going to ask you about the vacant defect, you are going to say that in case of non-ionic crystal, what we get to see, that there are few particles which are missing from their position, and we get to see vacant spaces in between. So when we get to see vacant spaces, that means the mass per unit volume is lost somehow, and therefore the density decrease, and this is the vacancy defect. Right. Now second is the interstitial defect. So what we get to see here, as the name suggests, interstitial means the vacant spaces between particles. Vacant spaces between particles. So that means this is a defect which is you can say, which is concerned with the somehow the vacant spaces which is present between the particles. So what we get to see here, again I am drawing a crystal, just look at the board carefully. Suppose we have a crystal like this. So what do I get to see in this? I get to see that in this is the interstitial space. I get to see the particle occupying an area between this interstitial spaces also. That means particles are in access actually. They are not missing from their position. Just keep in mind, they are not missing from their position. We get to see extra particles which are occupying the interstitial sites. So there we were, there we get to see that there were vacant spaces. That means the particles were missing. But means if their actual number of particles should be 10, but due to vacant spaces it was 7, suppose, right. So in this what we get to see, that if the particle should be 10 but they are not 10 actually, and they are not even missing from their position, but the extra particles are there. So suppose it has to be 10, but unfortunately they are 13 or 14. That means those extra particles is not disturbing the, you can say, the lattice structure, but they are disturbing the lattice. That is because they are occupying the interstitial space, as you can see. So what happens, that mass per unit volume increase in this case as the number of particles increase. So obviously density gets increased. Again, when we talk about that which kind of particles show this kind of defect, so again the non-ionic one. Right. So these two are almost similar to each other. So in this defect you get to see that particles missing from their position, and here you get to see an extra particle occupying the interstitial sites. And here, because the particles are missing, so that obviously mass per unit volume gets decreased, so that we say density decrease. Here particles are increasing in number, so we say that the density is somehow increasing. And both of them are shown by the non-ionic solids. Right. So this is the vacancy defect, and this is the interstitial defect. Now our concern is with the Frenkel defect, right. So what is actually a Frenkel defect? So first of all you should know that Frenkel defect is shown by the ionic ones, means the ionic solids, right. So what do we get to see in this defect? Just look at the crystal what I am making, or what kind of imperfection I just want to show you. So it is like this. Suppose I'm drawing a NaCl crystal, right? So let us take an example of NaCl. As you know, Na is positive and Cl is negative. It is smaller in size and it is bigger in size. So I'm drawing the Na like this. That means the smaller one, and my Cl is again the bigger one. Right, this I get to see here. So what happens, I'll write here which is Na and which is Cl. Obviously the smaller ones are Na and the bigger ones are Cl. So what we get to see in this defect, actually for this defect to occur there is a limitation, right? The limitation is that Na and Cl negative or any other cation and anion should have difference in their sizes. That means one should be bigger and one should be comparatively smaller. Then only you can get to see this kind of defect. So this is the limitation for the Frenkel defect to occur. That means difference in the size of the ions, right? That is the cation and the anion. Then if there is a difference between the ions, what we get to see here, we get to see that some of these smaller size ions, that is I'm talking about the Na one, right? They get dislocated. That means they move from their place and they escape to the interstitial sites. Suppose I am just moving this Na and this Na to the interstitial sites. And what happened? When they move from their place, when they get delocalized to the interstitial space, they occupy the interstitial state, leaving behind their own space. So that is why this is somehow appears to be a vacant space. So that means vacancies are created in a crystal. So this is what is the Frenkel defect. But as far as the density is concerned, so in this no other particle is going to be added or no particle is you can say either eliminated from it. So that means in this case number of particles are going to be same in order to maintain the neutrality. So even the positive and negative charges are same and even the number of particles are same. So that means there is no increase in the particles. It is just the delocalization of the ion, positive ion or the smaller size ion from its position to the interstitial space. So density is going to remain same in this case. It won't be affected, right? So these are the three defects. Again, vacancy, some particles missing. Interstitial, you get to see few more particles occupying interstitial sites, and in this case what you get to see that the positively charged or you can say any ion which has a smaller size get delocalized, and where does it move? It moves to the interstitial space, and the place which is left by the ion is just a vacancy, and that means we get to see positively charged ions occupying the interstitial space, and there are the vacant spaces which are actually seen from where that ion has moved. Right, so that means we get to see the positive ions occupying the interstitial space and we get to see the vacant spaces as well. But keep in mind that the number of particles, the charges, positive and negative are almost same. So that is why we don't get to see any difference in the density. Density remains the same. This kind of defect is shown by many other ionic compounds like AgCl, AgBr, AgI, zinc sulfide and many more. Right. So the limitation is only that there should be difference in the size of the cation and the anion. Next we have is the Schottky defect. Right. Again, the Schottky defect happens in case of ionic solids. It happens in case of ionic solid. So what do we get to see here in case of Schottky defect? Again, I am just making a crystal. See, this I am making a crystal. So, and you know that as I told you, it happens in ionic solids, so obviously they are going to be a positive and the negative one. And these are the interstitial sites, right? Now, if I say that in this some of the positive charge is lost, right? As we know that in case of solid, number of positive is equal to number of negative in order to restore neutrality. It is already there and proved. We know that, right? If I say that some of the positive charge is lost, not moved, I say lost, right? So that means this solid will acquire, if it is lost, so it is going to acquire the negative charge. That means it will no longer remain neutral, it will become negative. And if I say that it has lost excess negative charge, then you will say that again the neutrality is disturbed and this particle will become the positive now. But in lattice, however, we know that the neutrality is restored, that is the positive ions are equal to the number of the negative ions. So what happens in case of this defect? In this defect, equal number, keep in mind, right, we have to restore the neutrality. Equal number of positive and negative ions are missing from their position. Suppose I say this is a lattice and here I get to see the equal, like if I have lost one positive and similarly the one negative is lost from this crystal. So we get to see a vacant spaces, and those vacant spaces are just created by the equal number of the positive and the negative ion. Say if two positive ions are missing, so simultaneously the two negative must be missing from the same place. So that means neutrality is restored. Keep in mind, neutrality is restored. Equal number of positive and negative ions just gets, you can say they are not present actually, and they are and they just create the vacant spaces behind. So this kind of defect is shown by the Schottky defect. Now as the equal number of charges are missing, so that means neutrality is restored. Right, but when we talk about the density, so like the same way the number of particles which should be present are not actually present, that means mass per unit volume gets decreased. So that is why the density also get affected, it decreased. Otherwise in this case the number of particles remain same, it was just the delocalization, right, of the positive ion. Here what is there? We get to see vacant spaces, but because the equal number of positive and negative ions are missing from their position, right? So when they are missing from the position, they are creating the vacant spaces, but the vacant spaces created by the positive and the negative ions are exactly same in order to restore the neutrality. So that is why, but when we talk about the number of particles, they are not actual number of particles are present, which should be present actually, right? So that means mass per unit volume decrease and therefore the density also decrease. Again, it is shown by the ionic solids, right? So this is what is the defect. For example, I say it is shown by NaCl. It is also shown by AgBr. See, AgBr show the Schottky defect also, and it can also show the Frenkel defect, right? So these are the stoichometric defect. As I told you that point defect is divided into three categories. One was the stoichometric. These are the subcategories of stoichometric, right? And other is the non-stoichometric, and other is the impurity. We are done with the stoichometric effect and their types, but we are still left with the non-stoichometric and impurity. This will be taken in the next session. Just look at the